Unlike other preparing buffer solution problems, where you have a strong and a weak, you would add them on the same side as reactants because they react stoichiometrically. But if you're mixing a conjugate acid and a conjugate base together, the process is different in that you don't, even though you're mixing them together, you're going to write them on opposite sides of the equation. So the question we'll be doing today is, what is the pH of preparing this buffer solution? And we know that the equation for the pH of any buffer question is a pKa, which is a negative log of the Ka plus the log of the concentration of the base divided by the concentration of the acid. So we're given this problem with these following information. If we're mixing these two together, that means we're going to have a total volume of 250. And we'll start by finding their molarity. And their molarity is the C equals NV, N equals CV concentration times volume. And use volume as liters will give you 0.015 moles of this base. And here, I actually did this one wrong for a very silly reason because I didn't type it properly into my calculator. I wrote my answer was 0.3 instead of 0.03, and that just messed up the entire question, even though I tried it 2 times. So be careful on that. Okay, now we're going to find out which way they're going to react, and Q is telling us that it's going to be 0, which is smaller than the Ka. That means it has to shift to right. So right now we're just doing the ice table way, the long way of solving this problem. The short way is just to throw in the moles or the concentration. But if you want to throw in a concentration, you have to use a total concentration with a total volume, okay? So let's finish this first while we still remember to do it. So the Ka is going to be given on your formula sheet. And on mine it says it's okay, so hang on. So I have the Ka, but here I wrote the equation in the other way. I wrote it in a way where we need to use Kb. So instead then we need to use Kb is equal to Kw divided by Ka, which is 1 times 10 to the negative 14 divided by 6.3 times 10 to the negative 5, giving us 1.587 times 10 to the negative 10. So with the Kb, we can then throw in these values here, and the rest is just like an ice table problem. And make sure to use the assumption and to check the assumption later on that X is negligible. And when you find X, that is the concentration of hydroxide, and then you can use POH is equal to negative log of hydroxide, and that will use 14 minus this to get your pH. Now let's try the Henderson-Hasselbalch way. So there are 2 ways we can do it. The first one is use the concentration, and the second one is using the moles because the volume will cancel out. So the moles of base that we have, okay, hang on. So notice how I wrote this equation. No, it's okay. Okay, the moles of the base, 0.015 moles divided by 0.03 moles. And then I throw all of that in. This is log. So this log part is all together giving me a negative 0.3. And if I use a pKa, which is a negative log of 6.3 times 10 to the negative 5, and then plus what I got, I get a pH of 3.89, 3.9. So that's one way you could do it. Now the other way to do it is use a concentration a little bit longer, but whatever. So yeah, honestly, it's just the same thing, except you put divided by 0.25 liters and then 0.25 liters So really these two just cancel out. So you have two ways of solving a buffer pH problem. The first one is to use a Henderson-Hasselbalch, the easy way, and the longer way, if you need to show your work, is finding the Ka or the Kb, solving for x. And just a special note to remember that if you accidentally wrote the equation in the reverse direction and need to use a Kb instead, don't worry, it's gonna be the same answer as a Ka. I did make another video on that, but I can't find it anymore, where I showed absolutely how those things are the same, but just go with it. Trust me, it's right. As long as you don't accidentally write 0.3 instead of 0.03, unlike what I did. Good luck.